All right, we're going to look at another model here. This is a mixing model. So we have a tank with some water in it. We've got a solution, salt solution coming into the tank. We've got the mixed solution leaving the tank. And we're supposed to write a differential equation that models the situation and use that to answer some questions about the situation here. So the first thing that we want to be sure that we do is label what our variables represent. I'm going to use S, which is a little dicey sometimes to use in an equation because it looks a lot like a 5. So if you prefer not to use S, then that's okay. But I'm going to use S for the pounds of salt in the tank at time t. And I'm going to let T represent, let's see here, the information in the problem looks like we're given in minutes. The rates of change are given in gallons per minute. So I'm going to let T equal the minutes since the solution started coming into the tank and the drain was open and everything was going out of the tank. All right, we do have an assumption here that we have a perfectly mixed solution at all times. That may or may not be true, but that does require some partial differential equations, a diffusion model, if you want to really model the different elements of salt at different levels of the tank. So we're not maybe quite ready for that yet. So that's something to look forward to when you take a partial differential equations class. All right, so we want to write down this differential equation. So we're going to look at the rate of change of pounds of salt per minute. So my differential equation is going to be ds dt. And I'm going to put a little label out here to the side just to remind myself that this should be in pounds per minute. My unit should be in pounds and minutes here when I set up my differential equation. All right, so ds dt equals, and then we want to think about what's changing in the tank here. So we've got some salt coming in the tank. We've got 1 pound of salt per gallon. Units will help here. Notice that this is pounds per gallon. Pounds per minute is what I need, so I need to be careful about that. That's entering the tank at 2 gallons per minute. So that's a positive, increasing the amount of salt in the tank. So this is a positive rate of change. 1 pound per gallon at a rate of 2 gallons per minute. And just like you do use unit analysis when you do a science problem in physics class or chemistry class, just thinking about those units. So we've got the right units here, pounds per minute on this term. So this is for the water or the solution that's entering the tank. And then we've got something leaving the tank too, right? So we need to think about that here. So we've got the perfectly mixed solution leaving the tank at 3 gallons per minute. So that's going to be decreasing the amount of salt in the tank. So we'll have a minus here. 3 gallons per minute. So that doesn't quite give us the right units here. So I need to think a little bit about what's happening on this term. So the amount of salt in the tank is changing. This amount of salt that's coming in is fixed at 1 pound per gallon. But when we're draining fluid out of this tank, the amount of salt in pounds is a variable. That's our variable here. So we're going to have S pounds per, and then we need to think about how much fluid is in the tank. So we start with 60 gallons, and then we have fluid going out. So let's think about this a little bit over here. So the amount of gallons in the tank at time t will be 60 gallons minus, that's going to start at 60, but then it's going to decrease. We have 2 gallons per minute coming in, 3 gallons per minute going out. So that's decreasing by 1 gallon per minute times t minutes. So this expression here, 60 minus 1t, will tell us how many gallons are in the tank at time t. The reason I have minus 1 here is because we had the 2 gallons per minute going in minus the 3 gallons per minute in minus the 3 gallons per minute out. So that's a net change of minus 1 gallon per minute when we have that flowing out. Okay, so S pounds per 60 minus 1 T, 60 minus T gallons. Okay, so again, paying attention to units here, pounds per gallon, and then that's going out at a rate of 3 gallons per minute. And so our units here, we're good. Gallon, or we have pounds per minute on all of the terms here. All right, so there's our differential equation. There is also an implied initial condition here in this problem. So the tank initially contains 60 gallons of pure water, which means there is no salt in the tank at t equals 0. So we can write an initial condition S of 0 equals 0, 0 pounds at t equals 0. All right, so now we have our differential equation. So now we can just solve that to answer the question. ds dt equals 2 minus 3s over 60 minus t. And then we have our initial condition. So here's our simplified differential equation. So now we want to solve this. So thinking this through, linear, separable. This one is linear. So it is not separable, but it is linear. So if I want to rearrange the terms so that I can put it in standard form for solving a linear differential equation, I'm going to add this term to both sides, and I'm going to rearrange the constants a little bit on that. 3 over 60 minus t times s, so that I have it clearly function of dependent variable times function of independent variable times dependent variable equals 2. All right, and then I can use that to find my integrating factor. So we've done this a lot of times at this point. Rho equals e to the integral of 3 over 60 minus t dt. So technically there's a little u substitution there when you do that. So you'll get e to the 3 times the natural log of 60 minus t all over -1. So we'll make that -3 ln of 60 minus t, technically absolute values there. And then you want to simplify this, so you can use that exponent property of logarithms here to bring this exponent up here, and then the exponential function and logarithm function undo each other. So we get 60 minus t to the -3. So there's our integrating factor. That's what we're going to multiply through by, and so I'll go ahead and write that in that simplified form. So we'll go ahead and distribute through 60 minus t to the -3 ds dt plus, all right, and then when I take 60 minus t to the -3 times this term, we'll get, I've already got this 60 minus t to the -1 power essentially here. So we're going to make that plus 3 times 60 minus t to the -4 s is 2 times, remember to multiply this right-hand side. I tend to forget that, so don't you forget it. Okay, so 60 minus t to the -3 times the right-hand side. And again, the whole point of doing that is that you force a product rule on the left side, so you can check that. But you should end up with a derivative with respect to t of whatever your integrating factor was times s. Right, and so you can double check that and think about how that would work with your derivative. You might have to think a little carefully about why you have a plus 3 here instead of a minus 3, but there's a little chain rule. You get an extra minus sign from chain rule there. So you can verify that that is indeed the correct form. Integrate both sides of this with respect to t. I don't mind if you don't write this step out, but you should understand that that's what you're doing at that step, integrating both sides with respect to t. So on the left side, the integral and the differentiation undo each other. And then I need to go ahead and integrate this on the right-hand side here. So we're just basically going to be using power rule. So we'll have 2. And then technically there's a little u substitution here. So I'm going to integrate my u to the negative 3 power. So I'll have u to the negative 2 over negative 2. My u is 60 minus t over negative 2. And then times a negative 1 from my chain rule here. So that would be a plus. All right, so at the next step that I'm going to do here, I'm going to go ahead and divide through by 60 minus t to the negative 3, or multiply through by 60 minus t to the positive 3, so that I can solve this for s and have an explicit solution. So my 2's will cancel here. When I take 60 minus t to the positive 3 times 60 minus t to the negative 2, we will just have 60 minus t, 60 minus t, and then plus c times 60 minus t cubed. All right, so there is my explicit general solution. I do have an initial condition, so I can go ahead and plug that in and find my c value here. C times 60 cubed, so subtract 60 and divide through by 60 cubed. You get negative 1 over 60 squared, and so we'll write our solution here. All right, so here is one of the things that we were asked to find. The equation, the solution to the differential equation that models the amount of salt in the tank at time t. The other thing that it asked us to do was we were asked to determine the maximum amount of salt in the tank and when that occurs. So I'm kind of a little bit out of space here, so I'm not going to write out all the work for that, but we'll just talk through how you would do that. So this gives the amount of salt in the tank at time t. If you want to find the maximum amount of salt in the tank at time t, then essentially that's really going back to what you learned in Calculus 1, Calculus 1, where you would want to maximize a function. So this gives the amount of salt in the tank at time t, but the next part of what you were asked to do is you want to find when is this maximized. So you're essentially going to look at when the derivative of this is equal to 0 and solve for t. So we're going to find that derivative. We're going to differentiate this with respect to t. You might notice I have a ds dt over here, but I really want this given completely in terms of t. Notice that this one involves an s here. So we wouldn't really be able to use this to answer that question. But we want to find ds dt here. And then you're going to find critical points. You're going to set that derivative equal to 0. You're going to find your critical points. You're going to test them to determine whether they give a maximum or a minimum value. And then you're going to use that to answer the question. So when you do that for this one, you should get that occurs. You get a maximum value of salt in the tank of 40 square root of 3 pounds at t equals 60 minus 20 square root of 3, what was our unit of time here? Minutes. All right, so that should be your maximum value. So you should try that. Go ahead and find that derivative, set that equal to 0, and solve for s and solve for t, and then test that, and then that gives you your maximum value there. All right, so try some of these mixing problems. They're all kind of fun. They're usually pretty easy differential equations to solve, so as long as you can get it set up correctly, you're going to be good. I always say units are your best friend on these problems. If you can pay attention to the units and just think about what's going into the tank and what's leaving the tank, and be sure that whatever's entering the tank is going to be a positive rate of change. Whatever's leaving the tank, you're going to have this subtraction here. You should be able to get the differential equation set up right. And then from there, you know how to do the solution. So try some homework problems like that.